right, these are notes number 6, section 7.1.3 on coordinate geometry. And basically by that I mean by coordinate points, think of like graphs, axes, and everything like that. In geometry, think about your shapes. So we're going to tie our shapes in with the stuff you learned in algebra. So let's quickly backtrack and give you a history lesson on algebra here. Slope-intercept form is the form when you are given a slope and a y-intercept, or that's what's given in the equation. So you can convert another equation to it, which we'll do at least once here, and then use that information to graph something. So the formal equation is y equals mx plus b, and m is your slope, and b is your y-intercept, because, as we all know, y-intercept starts with b. I do not know why they have that, but you know that you can't use y because they use x and y as the coordinate point that you use that's a solution to your particular equation. So you can't use y, obviously. Okay, your slope is defined as your rise over your run, which means how high up do I go with respect to how far over I go. That's why you can't have a slope that's completely vertical, because if you have no run, that means you have 0 run, and you can't have a rise of something over 0. So that's why slopes there are undefined, because you cannot divide by 0. Anyway, it's the change in your y values over the change in your x values. So how much do I change from a point here to a point here? How much do I go up this way versus how much do I go over that way? And mathematically speaking, if you have 2 points, you can define the slope, because it is a straight line, as y2 minus y1 over x2 minus x1. So if you have 2 points, x1 comma y1 and x2 comma y2, you can determine the slope between those 2 points. And it doesn't matter if you do y1 first, as long as you do x1 first as well, because you want to make sure everything's negative and positive as they're supposed to be. Okay, and your y-intercept is the location. I'll just put 0b. It's the actual coordinate point where your graph crosses the y-axis. The only place I ever use the word intercept is in terms of football. Once it, I mean, there's no real thing that I can tie into that, because interception's a turnover, and this isn't exactly a turnover, but it's a point of intersection, maybe where the football and player meet up. Okay, so in y equals mx plus b, if it's this one right here, y equals 2x minus 4, I'll start to do some examples for you. My y-intercept, I'll just put it right now, is 0, negative 4, because b equals negative 4. So the location of where I'm actually going to cross the y-axis is 0, negative 4. And I do apologize if it seems like I'm going too quickly with this lesson, because this isn't an algebra lesson by all means. This is just an intro. This is a backtrack to it. My slope is my rise over my run, and my number is 2 here, but 2 is also the same thing as 2 over 1. And always think of slopes like that if you can, so that way you know how far up do I go versus how far over I go. So I go up positive 2, and I go over to the right. We consider that positive 1. So from this point, I can go up 2 over 1, up 2 over 1, up 2 over 1, etc. I can keep going. And I could go the other way as well, as long as if I go down 2, then I go to the left 1. Down 2 to the left 1. That's the reason why when you do y2 minus y1 over x2 minus x1, they stay the same. Because if I did it the other way, I would have negative 2 over negative 1. And as long as the signs remain consistent with how they're supposed to, then I'm in the clear. And this graph, let's do a big old green line here. Should look a little bit like that. Okay? So there's the graph for y equals 2x minus 4. And my slope, I should rewrite it here, is 2 over 1. Okay, y equals negative x plus 3. My y-intercept is at 0, 3. We know that. Okay, but my slope. I don't see a number in front of here, but if you remember anything with algebra, Assume that if there's no number written in front of a variable, then that number is 1. Now in this case, there's a negative in front and no number, so our slope will be -1, and -1 is also -1/1. So when I start from my y-intercept, 0, 1, 2, 3, this time when I count, I can go up -1 or down 1 and to the right 1. Down 1/1. So when your slope is positive, it should go up and to the right. When your slope is negative, it should go down and to the right. When your slope is 0, it should be horizontal, left and right. And when your slope is undefined, that means your graph goes up and down. Okay, and the graph looks like that. And I'll draw my lines here, make them red, and off to the races. It's good to use a ruler in these cases, unless you're very precise. Now, y equals 1/2 x. Okay, this time I don't see my y-intercept, but if it is y equals mx plus b, I see my m and I don't see my b. Now here's another thing, if a piece of information is missing, you must assume that it's 0, and that's what's implied. So if it's 0, because this is y equals 1/2 x plus 0. So if it's 0, then I'm at 0, 0 for my y-intercept. And my slope is 1/2. Now don't let fractions turn you away here, especially with slope. It's actually just as easy as any other thing because you're still counting how far you're going. Here we want up 2/1. This is a fraction. This is a fraction. So is this. So we'll go up 1/2, up 1/2, etc. I'll go down 1 and to the left 2. And then my final graph should appear like so. Okay. There's my brief lesson again, going over those examples. Okay, parallel lines. Those occur when two equations have the same slope and different y-intercepts. Okay, so if I'm looking at something that's parallel, and you know what parallel means, same slope, so it never intersects, so we need something that has the same slope here, but it can't be the same exact line. That's why we need a different y-intercept. So even if it's over here, boom, these lines are parallel, same slope, which is 2/1, but different y-intercept. In this case, it's 1, 2, 3, 4, 5, 6. So the equation of this line is y equals 2x plus 6, which would be right there. Okay, so that's how parallel lines work. That's a 6, not a B. And same thing with these other guys. As long as my slope is -1, then it'll be parallel to it. And as long as my slope here is 1/2, then it will be parallel to this. And as long as, again, different y-intercepts. If I have the same y-intercept, then I have the same exact line. So going here, if I'm going to write equations parallel to the following lines, they want to tell us, so actually before I even do this part right here, let's just do another one. Y equals, as long as it's 1/4 x and not this, I could do plus 2. That's okay, right? But if they give you more information, it says that pass through the point 4, 1. So what I'll do here is, I know that my equation is some sort of y equals 1/4 x plus b, but I don't yet know what the b is because I need a line that specifically passes through this point. So in order to get that, I'm going to use my x and y that I know, and I'll substitute it into this equation. And then that'll help me determine what my b is. And then whatever that is, I'll insert back into the equation. So here, my end equation will be y equals 1/4 x plus something. And I want to know what that will be. Okay, so let's plug in 1 for y and 4 for x, because this is a solution to this line, apparently. We just don't know what the line is yet. So y equals 1/4 times 4 plus b. 1/4 times 4, 4's cancel, you get 1. So b, so 1 equals 1 plus b. Subtract 1 from both sides, you get b equals 0. So if b equals 0, my equation is y equals 1/4 x plus 0, or even better yet, y equals 1/4 x. Okay. This should be a pretty standard recollection of what we're doing here. I just needed the line that is parallel to this one, yet it passes through this point specifically. Okay. Now this one's a little bit different because it's not yet in slope-intercept form. So to transform it, we need it in y equals mx plus b. So in order to do that, I want to solve for y. And I want to get my x term first on the other side. So I'll have 6y equals negative 6x minus 2. Divide both sides by 6, I get y equals, I think this was supposed to be minus 12. Let me actually do that now because I want to get better numbers. Y equals negative x minus 2. So I'll change your notes on that. Okay, y equals negative x minus 2. So here's my equation. I need the slope of a line that passes through that as well. So here's my original line. I want one that has a slope of negative 1, so a negative x plus something. We need to figure out what that b is. So in order to do this, let's plug in one solution to the equation, 4, 1. Plug in 1 for y, 4 for x, so negative 4 plus b. And b equals, add 4 both sides, b equals 5. So your equation is y equals negative x plus 5. Again, parallel to it. Parallel to this line and this line, because these are the same thing, assuming that's a negative 12. And they're different y-intercepts. And final one here, the only difference in this one is I have to distribute first and then combine like terms. So I'll get y equals 2x minus 12 plus 10, or y equals 2x minus 2. I'm not going to ask you to transform these guys specifically. This is just a good rehash. It's just good to know. You want to get to this form because you want to know the slope and y-intercept. Okay, and again, we plug in one solution to the equation because we want it to pass through this point, or this, we want this equation to pass through this point. We want it to be a solution to it, and we want it to be parallel to that. So same slope, 2 over 1. Plug in 1 for y, 4 for x, and plus b. I'm sorry, 4 for x, 2 times 4 plus b. 2 times 4 is 8. Subtract 8 from both sides. 1 minus 8 is negative 7. So you get y equals 2x minus 7. Again, same slope, different y-intercept. Okay, perpendicular lines are, you know what they are. They're the right angles. Okay, they occur when slopes of two equations are opposite reciprocals of each other. Now, all that means, these two words mean different things. The word opposite, it doesn't mean negative, because if your original number was positive, you want your other one to be negative, but if it was negative, you'd want it to be positive. So you switch the sign of your slope. Reciprocal means the inverse. It means taking whatever number was on top, putting it on bottom, and vice versa. I'll give examples immediately and kind of let you see it from there. And again, I don't know if this is supposed to be minus 12 or not. We'll see how these go. I kind of just want to do one of them for the sake of time. You can fill out the rest, but really you need to fill out the rest. Make sure you try them for yourself. So let's see how this one ends up panning out. Write equations perpendicular, not parallel, to the following lines that pass through the point 0, 3, and determine where the equations intersect. So you have to do two things here. This last part, don't forget this part. I want you to know where these points meet. Now they might be fractions. I haven't tested these yet. I just wrote this up. So I have one equation, y equals 1/4 x plus 5. And if I wanted to graph it here, you don't have to. I just want to give you an example. Here's 0, 5, and 1/4 kind of looks like this right here. I'll go up 1 over 4, up 1 over 4. Right? So my other equation will not only pass through the point 0, 3, which is right here, but it will also have a slope that will run perpendicularly to it. So it's going to look something like this. So I want to find well, close enough. So I want to find the slope and the y-intercept, and then I'm going to find out what this point of intersection is. And like I said, it's probably going to be a decimal or a fraction. Okay, so here's my original equation. Now my slope is 1 over 4. So the slope of the perpendicular guy will be the opposite reciprocal. So I'll take 1/4, positive 1/4. I'll change the sign, so it'll be negative 1/4. And I will flip these two guys right here. So I will end up with negative 4 over 1, or better yet, negative 4. So the opposite reciprocal of 1/4 is -4/1. That will make this slope. You can tell here, I go down 4 over 1, down 4 over 1. Okay, and that's the difference between those. That's what makes them perpendicular. So if you ever need to prove something's perpendicular, figure out what the two slopes are and see if they're opposite reciprocals of one another. Anyway, let's go ahead and find out the equation of this line. So I do know that this is y equals -4x plus b. And I could waste time and plug in 0, 3 and figure, or 0 for x and 3 for y and figure out what b is. But we know what y-intercept means. The point that the line crosses through when it crosses through the y-axis. So it crosses through the y-axis at 0, 3. We know that it does. So if it crosses through there, we know that b is 3. So our equation is y equals -4x plus 3. We're done. That won't happen every time. It depends on what your point is that it's going across. Okay, but we're not done with the whole problem. We need to determine where the equations intersect. Now the equations intersect at the same xy value. And if they occur at the same xy value, and we already know what y is in both of these terms, let's find out what x is at that point, then plug it in for y. So if y equals this and y equals this, let's figure out when these two y's equal each other. And let's figure out what that x is. So let's set these two equal to each other. 1/4 x plus 5 equals -4x plus 3. And again, I'm sorry, this is kind of poor math here because I have fractions, but hey, you have to deal with them time to time. Subtract 3 from both sides, you get 2 over here. Subtract 1/4 x from -4x. This is -16 over 4 minus 1/4, so that's -17 over 4x. Divide both sides by -17 over 4. That's multiplying both sides by -4 over 17. Right? It's reciprocal. It's inverse. These guys cancel. And you're left with x equals -8 over 17. Not that fun math there. So whether or not you do these problems is beyond me. I can change these numbers up and help you out if need be. I think this is one of the only ones because this one is a fraction. Well, actually, the other ones will, I don't know. We'll see. Anyway, -8 over 17. So when x is -8 over 17, which is that point right there, -8 over 17, and you figure out what y is by plugging in -8 over 17 to one of these equations. I'll do it in this one. Maybe it'll make life a little bit easier. Y equals -4 times -8 over 17 plus 3. -4 times -8 is positive 32. So I get 32 over 17 plus 3, and 3 is 51 over 17. So 32 over 17 plus 51 over 17 equals 83 over 17, and that doesn't look like it reduces. So my final value here is -8 over 17 comma 83 over 17. And that number is a little less than 5. It's 4 and something. So and this is about -1/2. So it's about -1/2 and 4 point something. You're right, that should be close to 5. That should make sense. So I'm sorry for the weird numbers, but to each its own. Okay, and finally, you can plot coordinate points on a grid to create a polygon as well. So if you get points and you connect the dots, you'll get some sort of polygon. We're working with quadrilaterals right now, so we'll check out and see what kinds of quadrilaterals we get when we do this. Distances of diagonal lines can be found by using the distance formula, which I kind of went over in the other video, but unfortunately the audio was cut out, so we'll have to find another way to do that. I'll help you out with that at another time. We won't need it for this particular example. Diagonals of lines can be found by finding the, equations of each line, or of the lines between 2 points that are opposite angles of one another. So there's a difference between diagonal lines, right? So a diagonal line is something like that, and diagonals of lines. This should be diagonals of polygons. Diagonals of polygons. So if I have a polygon here, here's my diagonal. Whether or not it's actually diagonal, the fact that it goes across 2 different points is what matters most. So that should be polygons. Okay, Plot the following sets of points on the same grid and determine the names of the quadrilaterals. So we have to know the properties of these to know what kind of name it has. Then find the area and perimeter of each. I'm going to go ahead and use blue for the first one here. Let's plot these points down. A is negative 7, 1. So I go 1, 2, 3, 4, 5, 6, 7, and 1. There's A. B is negative 1, 1. Right there. C is negative 3, 4. And D is negative 5, 4. Negative 5, 4. And then you go ahead and you connect those dots. Let's make sure I'm not looking at a, there we go. So, now here's a funny thing. We always say figures aren't drawn to scale, and by and large these aren't exact, right? But if the graph is mapped one-to-one perfectly, like all these units are exactly the amount apart, and you used a ruler and you were so exactly precise that you could figure things out, then you can kind of trust things are drawn to scale. For instance, when I draw an altitude, and especially because this is a computer program, when I draw an altitude right here, because this will be important for one part of the question, for two parts actually, I can assume that I drew something that was a right angle from my base and my height here, h. Here's, by the way, this is a trapezoid. You can tell because these lines are parallel, and you know, and so here's where I'm going to draw from this, but I know these lines are parallel because I can see that they are, right? But we can't say things are drawn to scale. Graphs are a little different as long as you know they're on the same thing. Like here's negative 7, 1, negative 1, 1. They have no change in slope. As long as I know their slopes are 0, then it's okay. And as far as we can tell through our diagram, that's true. And this is the undefined vertical slope right here. So this is a reason why we can't trust diagrams are drawn to scale, because this is another reason, because you can use math to determine things as well. If you want to be so precise, use the math and figure it out. And my math says this slope is 0, this slope is 0. And this slope is undefined. And that's the opposite reciprocal, because 0 over anything, I'll just put x, its opposite reciprocal would be negative x over 0, and you know you can't divide by 0. Okay, so I have a trapezoid. I know that because I have one set, excuse me, one set of parallel lines. Now the formula for the area of a trapezoid, as you now know, is 1/2 times b1 plus b2 times h. So if I know the h, and in this way I can actually count because I have tick marks and I know exactly where I'm going from one place to the other. 1, 2, 3. So my height is 3. Whoops. What happened here? My height is 3. My b1 equals 1, 2, and my b2 equals 1, 2, 3, 4, 5, 6. Plug them in. Solve for a. A is 1/2 times 2 plus 6 times 3. So like a robot. A equals 1/2, 8 times 3. Okay, 8 times 3, because that's 8, is 24, and half of 24 is 12. So this is 12, and you want to leave units, 12 square units, right? These are each a unit. If they were in feet, we'd say 12 square feet. We're talking about area, our units are squared. We're talking about coverage, not just one dimension. Okay, I've ran out of room. Finding the perimeter. This is a little different because the perimeter is the outside boundary, and we don't yet know what these lines are. Here's where I will incorporate distance formula. I said I wouldn't, but I kind of will and kind of won't, because distance formula really is Pythagorean theorem. And I'll show you why that's true. All right, first of all, we know that b1 is 2, b2 is 6. We need to find out these two, and this is actually called an isosceles trapezoid, where both of these are the same length. So I'm just going to do it once, and then I'll call this C, and then I'll call it D for distance formula. Well, no, yeah, D. And then I'll figure it out over here. It'll be the same thing. Okay, as you can tell, this is a right triangle. I have to know this distance, which is 2, and this distance is 3. So D will be figured out with Pythagorean theorem. D squared equals 2 squared plus 3 squared. So d squared is 4 plus 9, which is 13. So d equals the square root of 13. Now it's not plus or minus because all lengths are, are positive. So my final perimeter, and I'll go back to distance formula in a second, but my final perimeter would be 2 plus 6, which is 8, plus root 13 plus root 13. 2 root 13s is 2 root 13. You can leave a decimal if you'd like, I guess. We're going to be simplifying things in terms of roots, I think, later, unless you've already done that in geometry. So there's my perimeter, and that's in units. 8 plus 2 root 13 units. And yeah, that does look kind of weird, and you might not want to see things that way. Maybe you do want to convert that into a decimal, in which case this is a little less than 4. So it's probably close to 8 plus 8. It's probably close to 15 units. Okay, back to distance formula here. D, because in case you didn't learn it or read up on it, okay, it's the square root of x2 minus x1 squared plus y2 minus y1 squared. You'll notice here, if I look at my points here, I look at these x values. This value is, what, -7, and this is -5. What I'm doing is I'm taking the distance between two x values, -5 and -7. The distance between them is 2, right? There's the distance between them, and then I'm squaring it. That's where I get 2 squared. The distance between my two y values, this is 4 and this is 1. I know I'm not using different colors, and I should, but the distance between 4 and 1 is 3. So I'm finding this length here, h, which is 3, and I'm squaring that. That's where I get 3 squared. And d squared is 2 squared plus 3 squared, but the square root of d is the square root of 2 squared plus 3 squared. It's the square root of the sum of the squares of the difference of my x values and y values. So I find the length by subtracting how far they are. I'm basically finding the distance between them. That's where distance formula comes from. And then it's the square root of it, and that's the hypotenuse of a right triangle. So all of these you can find by right triangles. Okay, I'm going to have to erase some work here because my last example cuts across this. So I'm going to do one more and then cut it out. And I'll go a little more quickly with this one because you just recognize one. I'll use green. E is 2, 2. F is 5, 5. And plus class is starting soon, so I got to cut this out. G is 8, 2. I think that's 8, 2. And H is 5, -3. Okay? And this guy, it might be this color green. There we go. Oh, I have to label all my other sides. By the way, I can find diagonals as well, and we're going to actually find the diagonals in this one. This guy is called E, F, G, H. Okay, we can use distance formula to find out these distances, but because, to save sake of time, these are the same length, these are congruent, and these are congruent. Okay, this is a kite. I know for those very properties. Sides near each other are congruent, two different sets of sides with congruent adjacent sides. Now I'm going to draw the diagonals here. Now they won't look diagonal, right? They'll just look normal. But I'll go ahead and make that dotted red again. I liked that. Here's one of my diagonals, and here's another one of my diagonals. It's called D1 and D2. Now, with a kite, my diagonals are always perpendicular to one another. Okay, this is D1, and this is D2. And the formula for finding a kite is actually solved by A equals 1/2 D1 times D2. I proved that last time. It's half of this rectangle, if I actually drew a rectangle perfectly. It's half of that, so if this is my base and this is my height, it's exactly half of my base times height. Okay, my D1 I'll count out 1, 2, 3, 4, 5, 6. D1 equals 6. D2 equals 1, 2, 3, 4, 5, 6, 7, 8. My area is half of 6 times 8, which is half of 48, which is 24 square units. That's area. Now perimeter, again, it's found the same way we found the other one. The distance between two guys. You can use distance formula and plug it in, or better yet, now that you have these things kind of written down, you can just use Pythagorean theorem for each of these. So this length, half of 6, is 3. So this is 3, this is 3. You'll notice, by the way, we talked about this property. I talked about this property once. These always bisect each other, so these are always congruent. These are not, by the way. This length is 3, and the other bit of 8 is 5, so that's 3 and 5. Now, these are 45, 45, 90 right triangles. I'm just going to save time. You can do a squared plus b squared equals c squared, but this is 3 to 3 to 3 root 2, I believe. That's how it works. And this should be the exact same because they're congruent. These guys all have to use Pythagorean theorem. 3 squared plus 5 squared is 9 plus 25, which is 34. Square root of 34 is the square root of 34. I don't think I can reduce that anymore. So these are both root 34. So my perimeter is 3 root 2 plus 3 root 2. So 3 root 2 times 2 plus root 34 times 2, which is kind of weird. It's 6 root 2 plus 2 root 34, and I'm sure there are easier ways for me to write that. I could have wrote root 17 root 2. That would have been really weird. Anyway, yeah, and these are in units. So we might want to make these decimals in class until we start simplifying these. I just don't have a calculator in front of me, so I can't do it right now. Okay? But there's the perimeter of my kite. So this was coordinate geometry. What we are going to do eventually is, like, I'm going to find these diagonals here. You might have to do it in your homework, actually, but find the equations of the lines of the diagonals. You find these points, you find the slope with those points. Let me go ahead and, in the beginning, write how you find the equation of a slope. Oh, this is it, y2 minus y1 over x2 minus x1. So take your points, subtract them, you'll find your slope, and then find where one of them crosses the y-axis. That's where you get the equation of this line right there, and the equation of the other line. You can set them equally to each other and see where they intersect. You can, sorry, I lost my place. You can find out if they're perpendicular or not by finding their slopes, etc. That's where we'll know properties of things, especially with kites, because they have to be perpendicular. Okay, hope this made sense, and I'm signing off.